Woohoo! Today we're going to look at Chapter 5, Exponential Functions and Logarithms. Yay! And specifically, we're going to start off with 5.1, Exponential Functions. Now, exponential functions are technically brand new for this class, but I'm going to guess that a lot of people have had some experience with them in the past. And certainly everybody, I think, at one time or another, if you're past algebra, has squared or cubed something. So this is going to have to do with functions where we've got an exponent, hence the exponential functions part. So an exponential function that we're going to be studying, the ones we're going to specifically look at, will look like this. And I wrote this out because my pronunciation is terrible. But f of x, I can do that fine, equals, also good, a, so far so good, to the xth. I have never been able to pronounce this properly, xth power. So that's how you set it up. To be honest, a lot of times when people are saying it, they'll just say a to the x because it's a lot easier. People understand when you hear the words to the, it means it's an exponent. Now, we're specifically going to study the ones where a is greater than 0. Now, you can look at what happens if a is less than 0. So in other words, if you've got a negative base, but the whole function goes flip-flopping around a lot, and it gets kind of bonkers to try to graph it. So we're going to skip those. If a were equal to 0, if you have 0 raised to a power, well, it's almost always going to be 0, except for 0 to the 0th, and then we'd be stuck with a missing point. And then we're also not going to allow a equals 1. And if you think about it, that kind of makes sense, because you raise 1 to a power, 1 squared is 1, 1 cubed is 1, 1 to the millionth is 1. And so it would be a not very exciting function to study. We could study it, but it would get kind of boring and repetitive after a while. So we're going to stick to the more exciting ones. And specifically, we're going to use these to model interest. Interest is what happens when you have a small amount of money and then it grows over time magically. And so how does it magically grow? Well, what happens is if you have a small amount of money and you put it in a bank, hopefully if you put it into a bank or a credit union or another investment, over time you will get little bits of extra money. Wherever you've put the money, they will pay you for that money. They give you a little bit of extra, which is called interest. And over time, the interest helps that small amount of money to grow. Compound interest is what happens when you've got a small amount and you get some interest and that makes it grow. And then you get interest on the new amount, and then you get a slightly more interest, and that grows more, and then more interest and more interest till you've got billions and billions of dollars, which is awesome. Now, that's as much explanation as I'm going to do right now, just with my hands. What's going to happen is we will study these formulas very carefully and specifically with examples in Chapter 6. So weirdly enough, in Chapter 5, I'm going to say we don't really have to know what the formulas mean. We're going to focus on what the mechanics of the mathematics is. So we're doing it a little bit backwards. Normally, we talk about what the meaning is and then how to do it. And this time around, we're going to talk about how to do it first. And then once you feel comfortable in Chapter 5 with all of the mechanics of the mathematics, then we'll move on to the application. So here's an example. It's got a lot of brand new words. And again, honestly, this may be brand new to a lot of people. Do not panic. These can be approached in a very mechanical sense without actually having studied these. So let's talk it through. So we've got $10,000. If $10,000 is invested at 6%, and I'm just noticing, oh my gosh, what is that behind you? Is that a pterodactyl? Oh my goodness. Oh, I guess not. I guess it was just, I saw a shadow or something. Thought it was a pterodactyl in your room. Sorry about that. What? I don't know what just happened. Okay, let's go back. If $10,000 is invested at 6%, so that's the interest rate, $10,000 is the money we're going to start with, which we can talk about as the present value or the principal. You don't need to write these down. We'll talk about them more in depth in chapter 6. And it's compounded monthly. That means they figure out what the interest is every month and they give you the extra interest. This is really common for most consumers. If you are not a giant bank, I'm going to assume no one in this class is actually a bank, although that would be really funny, a bank wearing a trench coat taking a math class. But I'm going to assume most of you are students and not banks, in which case most of your interaction with financial instruments will be monthly interest. What gets calculated monthly in terms of interest? If you have a bank account or a credit union account, if you have savings or even a checking account that earns interest, or if you have a loan, if you have a car loan, a motorcycle loan, a scooter loan, or if by whatever chance you have a mortgage, all of these will be calculated, the interest will be calculated monthly. So basically we're just going to go in, figure out what the interest is for that month, add it on. Credit cards work this way too, right? Every month you find out, hopefully your balance is zero, but if your balance is not zero, how much extra money you owe, how much interest you owe for not having paid off your balance. Okay, so then the future value of the investment after X years is given by this formula. So future value just means what is it worth in the future? Okay, so future value is S in this case. Here's our initial investment, and then we got stuff here. So what I want to do is I want to, in part A, and this is not what the book does, but this is what I wanted to do, is I wanted to explain what each of the parts of this formula represent and then give a general formula for the future value. And I forgot to pull out some colors. You know how I love my colors. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Looks like we're going to be using all of them. Okay, so let's do S. So S is going to represent future value. And I know that because I'm teaching the class. And you know that because I've just told you that. It also says the future value of the investment after X years is given by blah. So we know that from context. Okay, next up, and I'm hoping that you're going to be able to distinguish these. I'm hoping this is pretty clear. It looks pretty clear on my video. Oh my goodness. I don't know what I was thinking. Whoa, is that another pterodactyl in your room with you? Be careful. Look behind you. Don't look at the screen. Okay, now you can look back. Hey, how about writing it out first? Oh my gosh. $10,000. Is the initial investment. Sorry about that, Sharktopus. Here. Sharktopus is going to be supportive, but just hang out. Notice you can learn a lot about support from Sharktopus. A lot of times what support is just being close. Not asking questions, not making demands, just hanging in every now and again saying, hey, I just want to check in. Is everything going well? And I'll say, yeah, Sharktopus, this is going great. I have totally not had to restart this video 15 times, and I'm feeling good about the world, hypothetically. Okay, so, and then Sharktopus is like, okay, I'm just right here. You know I'm here. I'm like, yes, I appreciate you being close, but not so close that I can't do my math. See, there you go. Modeling support. Everyone thinks Sharktopus is the bad guy, but in fact, Sharktopus is actually just a really supportive and sometimes, too supportive friend. Sometimes he gets, he gets too, he gets in the way of the math. So we just say, thank you so much for being close. We appreciate it. Okay, $10,000 is the initial investment. You don't know this, but again, this is the benefit of me having taught this class before and having learned stuff in the past. is the present value. Woohoo, that's what we're going to call it. And hopefully you're looking at these two going, really? It can't be that easy. And I'm going to say yes. Sometimes economics and finance is really that easy. Sometimes it's really not, but sometimes they're just like mathematicians. They name things exactly what they are, which is awesome. So that's the value right now. This is going to be the value in how many ever X years. Okay. Now I am going to skip the 1.005. Okay, because that is not going to be obvious what's going on there. So let's skip that one and go instead to the 12x So we know what x is. X is the number of years. But what is 12? And now I know in the video, if I just wait to hear someone respond, it would be a very long video. But I'm going to go ahead and I'm going to, you can't tell, I'm putting my hands on my temples and I'm listening psychically into the future to hear what you're saying. And Dora the Explorer style, I'm going to say, you're right. 12 is the number. Sorry, I'm running out of room, so I'm going to use that hashtag for number. The number of months in a year. Now, what is going on there? What the heck? Why is it 12? Why do we do that? Well, if we think about it, if it's 1 year, that's 12 months. But if it's 2 years, how many months is that? 2 times 12 is 24. So we have to multiply them together. So they're multiplied. And so why do we care about the number of months? Well, because we're compounding monthly. So we have to know how many times did they take the interest. Okay, now we have to go back to the 0.005. I got excited. I'm going to tell you, and this is why it's good to have a teacher around and not just try to figure things out without knowing. So thank goodness I have a use in the world. I'm going to tell you this is 1 plus 0.005. Now, if you've never done this before, you're going to say, well, duh, but what does that even mean? And I'm going to say that's 1 plus 0.06 over 12. And then you're going to say, what? And I'm going to say, exactly. And exactly. Why is this happening? And you can check this on your calculator. 0.06 divided by 12 is 0.005. So what am I doing? Well, if we go up here, we see that the 6% interest, this is why I'm using blue. The 6% interest is right there. And what am I doing? Well, I'm dividing it because it's 6%. That means 6% per year. So I'm going to have to divide by 12 to get... I'm sorry. I shouldn't just push Sharktopus to the side. That's not fair. Sharktopus is being so supportive. This is the interest rate per month. That's the little thought bubble there. The interest rate per month is the 0.06 over 12. Whereas the 6% that's up here, this is the interest rate per year. Woohoo. Okay, so 6% per year is 0.06 divided by 12 per month. Now, you should say to me, okay, that's fine, but what the heck is the 1 there for? And what I'm going to say, and I'm going to wave my arms, and you're all going to say, oh, okay, that makes perfect sense. And then we'll get to chapter 6, and hopefully I will make good on the fact that it will make perfect sense. So when we calculate these, you add 1 because you want not just the interest, but the original amount. Because when I ask you what the future value is, it's the original amount you invested plus whatever interest gets lumped in. So you want the original amount plus the interest. Here's the original amount. You're going to multiply by 1, right? 10,000 times 1, and then 10,000 times this. Now, you should say to me, wait a minute, there's an exponent, so you can't just use the distributive property. I say, yes, you're absolutely right. Good catch. But that's the way to think of it. The 1 is there to make sure that we get our money back. Okay? So, in general, what's the formula? Well, the formula is going to be S equals the present value. I'm just going to use a P for that. And then I'm going to do 1 plus the interest rate, and use R for that, the interest rate. So here's our R. Here's our present value, also principal, both P. It's very convenient. We're going to divide by the 12 months in a year because we know we're compounding monthly, at which point you should say, oh, well, what if we were compounding it yearly? Well, we divide by 1. What if we were compounding it weekly? Well, you either divide by 52, which is the actual number of weeks in a year, or some banks still use 50. It depends. I'm going to let accounting sort all that out. Math just tells you how to do the general form, and then thankfully accounting and finance will give you all the nitty-gritty rules and changes. I love math. It doesn't change much, 1,000 years of the same stuff. It's good. It's really awesome. Then up here, I'm going to include the 12 again. But this time, I'm going to include X. This is just 1 year. This is all the years together. So it's slightly different. And you're going to say, how could I have possibly understood or known to do that? And the answer is you wouldn't necessarily, unless you've studied this before. I'm walking it through with you. Or if you're just looking at the notes, then you're not listening to me right now. But I'd say if you were just going to look at the notes, hopefully the colors will help you see the parts. Okay? Shall we move on? Woohoo! I know we're at 18 minutes, but I'm hoping we can do this all in one go. So let's see how long it takes us. If it gets too long, I will switch over to a second video. But let's see what we can get done. So, find the value of the investment after 1 year. So what I'm going to do is I'm going to remind you, let me put this here, right there, what the formula was. We got the formula at the beginning. S equals 10,000 times 1.005 to the 12x, where x equals the number of years. Okay, so if it's the value of the investment after 1 year, x equals 1, yay! S equals 10,000 times 1.005 to the 12 times 1, which is 10,000, 1.005 to the 12th. Okay, let's get some calculating going. Yay! Let's cover up the ring light. No one wants the ring light. Let's dust off the bunny fur. Bunny fur, it goes everywhere. Everything is just soft all the time. I know, and Sharktopus is showing up. Sharktopus and the bunny get along great, unless Sharktopus falls on the floor. A couple of my puppets have fallen on the floor, and the bunny have found them. R.I.P. puppets. But Sharktopus is up here with us, where he'll be safe. So, we got to talk about exponents. Now, hopefully, at this point, you've got a calculator, because this is the sort of I'm not expecting you to do this by hand. You could. And if that's what you want to do, rock on with your bad self. But I'm going to recommend that we use calculators. Now, You can tell I love Texas Instruments. It is my thing. But Texas Instruments has two different ways they indicate exponents. And on the earlier designs, it was just this little pointy arrow up. You'll notice that looks just like on a keyboard, the symbol that's above the 6. So this is the exponent key, both on a calculator and on a keyboard. But in other versions of calculators, you'll see how it's very tiny, I know, but hopefully you can see it X to a box. Other types of calculators like Casio's and Sharp and all the other fun stuff, they may have X to the Y. They'll actually write out the exponent, so I think it's easier to find there. Here we're looking sometimes just for that up arrow. So you're looking for one of those. And I'm going to use this guy because it is, it's really nice. I can show you multiple steps and all. So I can go ahead and just type this in directly. 10,000. Now, these parentheses are just there to make it easier for us to do the multiplication. There is just the one term inside, so I don't have to use the parentheses, but if you feel like it, you could always just put the parentheses in. Now, if you don't, sorry, I meant delete, not clear. If you don't have parentheses, then you'll want to do a multiplication here. And then 1.005, and then I'm going to write my exponent right there, 12. Now, the great thing about the calculator is it will know the order of operations. It will know that the exponent comes first. And we get a grand total of 10,616,77812. And then we have to figure out how to round. And rounding is something that's going to come up in every problem. Look for what the instructions are, because there are going to be different instructions depending on which problem you're doing. Make sure you pay attention. And if there are no instructions, like here, go ahead and realize, okay, we're dealing with money, so American dollars are calculated to 2 decimal places in general. So I want to round to the nearest hundredth. So this is going to be, and I'm going to go ahead and put in my dollar sign because I'm using units here. $610,616.78. And you'll notice I did a little wiggly equals to remind anyone reading it that I have rounded. It's not an exact equal. With money, generally in investments, it's not ever going to be exact. Very, very rarely. Sometimes it will, but most of the time, no. Okay, so that's pretty cool. Notice we start with 10,000. At the end of the year, we got an extra $600. And we didn't just get $600, we got more than $600. So you can see that compound interest happening. Okay, 30 years. Yay! S equals 10,000. 1.005. And up here, we're going to do 12 times 30. Now, this is up to you how you do this. You can calculate this all in one go using a calculator. A lot of people, I think, would be more comfortable doing some of the math in their head or separately on the calculator. 12 times 30, and any of you who are already in the mortgage business, you know 12 times 30, because this has to do with mortgages. They tend to be 30 years long, 360. So I am just simplifying this. Do I have to do this step? No. But a lot of people will prefer doing the calculations like this. This is just, you get to choose whatever you'd like. 10,000. And then I'm going to go ahead and use the parentheses this time just to show you what it looks like. 0.005, close parentheses, exponent 360. Okay, equals. Ooh. Sorry, you can't quite see it. I don't know if you're hearing it, but in the background, I've got my back door open and I've got a little area in the back where my rabbit can run. And the rabbit and a squirrel are having a loud argument over some nuts. I put the nuts out for the crows, of course. So, of course, the squirrel and the rabbit are fighting over them. It's never a dull moment here. Okay, so how did we do? Oh my goodness. If we can wait 30 years for our money, look at how much interest, right? The original amount was $10,000. We've got over $50,000 in interest. Nicely done. Nicely done. So, what's the takeaway about this section? This section, you need to know where your exponent is. And you need to know how to plug in, know where the number of years go. But for the most part, most of the problems in this will not require you to understand anything. And hopefully I'll go over enough of these examples in chapter 5 so you'll be well prepared. One thing I wanted to do to end 5.1, even though I am hoping that you've worked on exponential functions at some time in the past, I want to use Desmos to graph this function. Now, because of the way I'm filming this, this is my way of doing this low tech. I actually this is so sad. I printed this graph out. And you can't quite see as much, but let me show you. We can talk about this. There is, I don't know if you guys can see it. I typed this in, and hopefully you know what Desmos is. And if not, just Google it. Desmos is a website. It is a graphing calculator, and it is free, and it is really, really powerful. It's also an app. I have the app on my phone. I'd show you, but I'm using my phone to record this right now. So it's an app that you can just have on your phone, and it is really surprisingly powerful. And so I wanted to talk about, review what the heck is an exponential function. A lot of people talk about exponential growth. Oh my gosh, the numbers grew exponentially. Well, most of the time, if you hear that on a news program or in media somewhere, they don't know math, and all the math teachers, you can hear us all weeping quietly in the corner, eating a lot of pumpkin bread and saying, "Oh, I'm very sad." But we will keep trying. We will keep trying. But you guys are going to understand what exponential growth is. Exponential growth always looks like this. It swings up. Notice that it looks almost like half a parabola. And now I am deeply regretting not having graphed a parabola here for you to see, because parabola is much shorter. Well, we could talk about it. It depends on the parabola. I will compare that, I'm sure, in a different video. I promise you that. I'll come up with some way to do that. I'll print that out. So here, what can we see? Well, we can see this awesome growth here. And you can't tell, but I'm going to point out that this point is at 0, 10,000. And what does that mean? Well, if this is the x-axis and this is the y-axis, then this means when x time, right, this is time in years, and y is in dollars, at 0, we've got $10,000. So you can see the intercept is that beginning point, and then you can see the money growing. And you can see that for the first 10, 20 years, it almost looks linear. This is very, very shallow growth, not a lot of growth. But notice that around here, it starts to pick up speed, and suddenly it just goes whammo. So if you can wait 30, 40, 50 years, that's when the increases start to get really amazing, right? You can watch Y just going up. Now, the next thing I want to talk about, the reason to print this out so you guys can take a look at it, is that this is the graph of this equation. This is math. Math is great, But this class is not just about math. This is also about the finance, the economics, the money behind it. Yay, money. And if we're using this graph in this application, then you'll notice that -20, -10, this makes no sense. This is talking like before we invested, we had less. And that may be true, but we don't know that. So in this case, for this particular problem, we would want to scratch that out, because this is before we started. And this is year 0, which is the beginning. Oh my gosh, I can't remember how many n's are in beginning. Just put in some number of n's and charge me. If I put in any extra n's, I promise I will give them back later. And if there are any missing, you can add in a bunch of n's. I'll probably fix it before I make a Xerox copy of it. Sorry, my spelling is terrible. But the year 0... Oh, I know! Look over there! Oh my gosh, the pterodactyl is back! Totally back. Don't even look at the screen right now. There we go. Start. Oh yeah, I'm sorry, false. Seriously, you've got a lot of shadows in your room that look just like pterodactyls. I thought you had a pterodactyl. Okay, so year 0 is the start. I don't know why I was trying to spell a word like beginning with like, there are at least 12 n's in it, right? So that's where we're going to start. And then at some point, if you were going to graph this, please put an arrow that says it keeps going. And then really, in a perfect world, you'd put arrows on everything so nobody gets hurt. These are like little ways of keeping these are like little cozies for the end of the line so no one pokes an eye or something. So we've got this graph which describes the growth of the money. So that's it, you guys, we made it. Even with as much as I was talking about everything, this is under 35 minutes. Yay! Woohoo! And for Sharktopus and myself, I want to say thank you so much for joining us. And, have a great day. Remember, you're awesome. And math on.